Today we're going to talk about a particular type of probability called binomial probability. Now this is finding the probability of what we call a binomial experiment. Now what is a binomial experiment? We're going to talk about that first. So a binomial experiment satisfies the following three conditions. First, the same experiment is repeated a fixed number of times, so it's an actual value. For example, we did this experiment 10 times. There are only two possible outcomes, either a success or a failure. And then the repeated trials are independent so that the probability of success remains the same for each trial. So since they are independent, that means that the result of one experiment does not affect the result of the next experiment. So the repeated trials are independent, so the probability of success remains the same for each trial. So the probability doesn't change between trials. All right, so binomial probability is found as the probability of x number of successes in n number of trials is equal to n choose x times p, that's the probability of the success, to the x times 1 minus p, that's the probability of failure, to the n minus x. So let's just write down what everything represents here. So p is the probability of success in a single trial of a binomial experiment. N is the number of independent repeated trials. X is going to be the number of successes, so p raised to the x. That's the number of times you succeed. And to find the number of failures, well, if you did this n number of times, you simply do n minus x to get the number of failures. Take a look at example 1. A recent survey found that 59% of college students attend more than one institution during their college career. Suppose a sample of 6 students is chosen. Assuming that each student's college attendance pattern is independent of the others, find the probability of each of the following. Exactly 3 of the 6 students attend more than one institution. Okay, so let's start by first writing out our binomial probability formula here. Now, 3 out of the 6 students attending more than one institution. We're going to call the probability that a college student attends more than one institution our success. So this would be 3 successes in, well, we have a sample of 6 students. So 3 successes in 6 trials. So that's 6 choose 3 times, now the probability that you get a student that attends more than one institution is 59%, so 0.59 raised to the third power because there are 3 students who are trying to get there for success. And then the probability that they did not attend more than one institution, that would be 1 minus 0.59, and we raise that to the 6 minus 3, the other 3 students. Simplifying this, we end up with 20 times 0.2054 times 0.06892. And multiplying that comes out to be about 0.28. So about 28% chance that exactly 3 out of the 6 students attend more than one institution. Let's try the next part. None of the 6 students attend more than one institution. So we here are trying to find the probability that there are 0 successes in 6 trials. So that would be 6 choose 0 times 0.59 to the 0 times 1 minus 0.59 to the 6. All right, 6 choose 0, that's equal to 1. 0.59 to the 0 is 1, and then we have 0.41 raised to the 6, and that ends up being about equal to 0.00475. So there is about a 0.475% chance that none of the 6 students that are sampled attend more than one institution. Let's try another example. Find the probability of getting exactly 7 heads in 8 tosses of a fair coin. So here we're trying to find a success as being getting heads on the coin toss. And in this case, we're trying to find the probability of getting exactly 7 heads in 8 of those tosses. So 7 successes in 8 trials. So x is 7, n is 8. Now we know what the probability of getting heads is if it's a fair coin. It's a 50-50 chance. So this would be 8 choose 7 times 0.5 to the 7th times 1 minus 0.5 to the 8 minus 7. So this ends up being about 0.03125. So this comes up to about 3.1% chance of getting exactly 7 heads in 8 tosses. All right, example 3. The Federal Trade Commission, FTC, monitors pricing accuracy to ensure that consumers are charged the correct price at the checkout. According to the FTC, 29% of stores that use checkout scanners do not accurately charge customers. If you shop at 3 stores that use checkout scanners, what is the probability that you will be incorrectly charged in at least one store? Now this one's a little bit different from the other examples because this is at least one store. So it could be one store, it could be at 2 stores, it could be at 3 stores. So what we're going to do is we are going to have to find the probability that 1 out of the 3 stores incorrectly charged you, 2 out of the 3 stores incorrectly charged you, and 3 out of the 3 incorrectly charged you. Once we've done that, then we can find the sum of those probabilities to find the probability that at least 1 incorrectly charged you. Okay, so let's go ahead and find each one. So the probability that 1 out of the 3 stores incorrectly charged you is going to be equal to 3, choose 1, times, now 29% of stores that use checkout scanners do not accurately charge customers, so that's our success, 0.29 raised to the first power, and then 1 minus 0.29 raised to the 3 minus 1, or second power. All right, the probability that 2 of the 3 is going to be 3, choose 2, times 0.29 raised to the second, times 1 minus 0.29 raised to the 3 minus 2. And then the probability that 3 of the 3 incorrectly charged you is going to be 3, choose 3, times 0.29 to the third, times 1 minus 0.29 to the 3 minus 3. And now that we've found all 3 of those probabilities, now if we add them all together, that's going to be the probability that at least 1 of the stores will incorrectly charge you. So adding that all up, this ends up being 0.6421. So that means that if you shop at 3 stores, the probability that you are incorrectly charged in at least one of those stores is going to be a 64.21% chance. Okay, if you shop at 3 stores that use checkout scanners, what is the probability that you will be incorrectly charged in at most 1 store? Now, at most 1 means either none of the stores or 1 of the stores, right? But not 2 or 3. So, let's write that out. Probability of at most 1 means the probability that none of them incorrectly charged you, plus the probability that 1 of them incorrectly charged you. So we're going to find the probability of each one, and then add them together. So the probability that none of the 3 incorrectly charged you, that's 3, choose 0, times 0.29 to the 0, times 1 minus 0.29 to the 3 minus 0. That comes out to be about 0.3579. Now find the probability that 1 out of the 3 incorrectly charged you. That's going to be 3, choose 1, times 0.29 to the first, times 1 minus 0.29 to the 3 minus 1. That comes out to be about 0.4386. And then adding those together, we end up with 0.7965. So the probability that you are incorrectly charged in at most 1 store is going to be about a 79.65% chance. All right, the next thing we're going to talk about is what we call Pascal's triangle. Now, Pascal's triangle is really just a way of arranging numbers into a triangle, and it helps us provide a quick way to find binomial probabilities. So with all these binomial probabilities, you've noticed that at the beginning you always have some sort of combination there. A quick way to find a certain combination without having to, say, type it into your calculator or plug it into the formula is to use Pascal's triangle. So Pascal's triangle is a triangular array of numbers that provides a quick way to find binomial probabilities. Here's how it works. So you start at the top of the triangle, and we're going to call this row 0. This is going to be 0, choose 0. Now 0, choose 0 is equal to 1, and the way that this triangle works is the next row is going to have 2 numbers. It's also going to be 1 and 1. Now from here, the way that you get each next number is you start off with a 1 on the end, always start with 1, and then in between, you're going to add 2 numbers from the previous row together to get the next row. So in this case, we start with the 1, and then you add the 2 ones that are in the row before it to get the 2, and then you end with a 1. In the next row, again, we'll start with 1, and then we'll add 1 and 2 together, and then we'll add 2 and 1 together, and then we'll end with 1. So this is going to be 1, 3, 3, and 1. Keep going. We have 1 to start. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then end with 1. Next row, start with 1. 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. And you end with a 1. All right, and then the next row, we have 1, 6, 15, 20, 15, 6, and 1. Now you can obviously continue this, but in case we want to actually understand how this actually applies to binomial probabilities, we said at the beginning that in this first row, which we're calling row 0, so I'm going to stop calling it the first row, I'm going to call it row 0. The next row would be row 1, next is row 2, row 3, row 4, and then you continue on and on. Now in row 0, that represents 0, choose 0. In row 1, this is going to represent 1, choose 0, and then 1, choose 1. In the next row, 2, choose 0, 2, choose 1, 2, choose 2. In row 3, 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Next, 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. And this applies to every single row. So if you have the triangle already written out and you just wanted to, say for example, quickly find what 5, choose 2 is, you can simply look in row 5, look at the third entry there because it's 5, choose 0, 1, then 2, and then know that 5, choose 2 is equal to 10. So without having to use the formula, without having to use the calculator, you can easily find any of these combinations that you might need for a binomial probability. All right, example 4. Use Pascal's triangle to find the probability in example 3 that if you shop at 6 stores that use checkout scanners, at least 3 will charge you incorrectly. Okay, we're going to use the same idea here. At least 3 means it could be 3, 4, 5, or 6. Now, we have to find each of those probabilities before we can add them together. Now, for the first one, probability that 3 of the 6 stores charge you incorrectly, we're going to have a 6 choose 3 in front, right? So 6 choose 3 times 0.29 to the third times 1 minus 0.29 to the third. Next, we have 6 choose 4 times 0.29 to the fourth, 1 minus 0.29 to the second. Probability that 5 charged you incorrectly, that would be 6 choose 5 times 0.29 to the fifth, 1 minus 0.29 to the first. And then the probability that all 6 of them charged you incorrectly, 6 choose 6 times 0.29 to the sixth times 1 minus 0.29 to the 0 power. Now, instead of having to find 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6, using your calculator or using the formula, you can go ahead and use Pascal's triangle and look at row number 6. Now looking at row 6, 6 choose 3, that's the one right in the middle. That's 20, then 6 choose 4 is 15, and then 6, and then 1. So we can go ahead and replace those right away. So 20, 15, 6, and 1. And now we can go ahead and simplify. So this is 0.1764, 0.0535, 0.0087, and 0.0006. Adding those all up, we get this is about 0.2374, so about a 23.74% chance that at least 3 of the 6 stores charge you incorrectly.